Hello everyone, welcome to lecture 30 of the online course on Introduction to Microwave and Optical Metamaterials. In this lecture, we will look into the modeling of microwave devices using metamaterials. So here is the lecture outline. We will go about discussing the modeling of microwave devices using metamaterials, and we will take up some examples of how 2D model of a microwave antenna with one layer wire composite metamaterials substrate looks like. So, we have seen microwave devices have evolved significantly over the past few decades, mainly driven by the demands of the next generation communication systems, sensing technologies and compact high performance components. Among these devices, antennas serve as the fundamental building blocks responsible for efficient transmission and reception of the electromagnetic waves. Now, with the emergence of metamaterials, which are basically engineered structures that exhibit unique electromagnetic properties which are not found in nature, you will see that the modeling and performance of microwave antennas and related devices have seen revolutionary enhancement. So, wireless technology has been growing exponentially since the beginning of this century, due to the applications in domains like e-health, IoT and also smart buildings. So, this first growth can continue if we develop smart antenna systems that can combat a widened spectrum with energy efficiency. So, they must be energy efficient, cost effective and also compact, and must function in diverse environments. So, chip packaging, human body and matching network, etc. So, they should be able to operate in all these different environments. So, one of the possible candidates for compact wireless antenna systems is patch antenna, right. So, a patch antenna, which is also known as a microstrip antenna, is a type of antenna with low profile and is often printed directly onto a circuit board. It basically contains a metallic patch, as you can see here, typically rectangular or circular in shape. It is mounted on a ground plane with a dielectric substrate in between, right. So, the patch, as you can see here, is basically the radiating element, which is made of a conductive material like copper, etched into a specific shape. It can be a rectangle, square or circle. Then you have a ground plane here at the bottom. This is again a conductive layer that acts as a reflector, and it provides reference for the radiating patch. And then you have a substrate, typically FR4 or Teflon is used, that separates your patch and the ground plane. Now, how this patch antenna works? Patch antennas operate based on the principle of resonant cavities. So, when excited by a feed, this is the feed point. So, it can be a coaxial feed or a microstrip line, which is shown here. The patch acts as a resonator, creating a field. So, the patch antenna basically operate based on the principle of resonant cavities when excited by a feed, typically a coaxial probe or a microstrip line, which is shown here. The patch acts as a resonator that creates a field between the patch and the ground plane. So, the edges of the patch, these ones, they basically radiate electromagnetic waves into space, creating the antenna's radiation pattern. Now, what are the advantages of using a patch antenna? The first thing is its low profile. So, it is integrated into a flat substrate, making them suitable for mobile devices, GPS modules and other compact applications. The another important factor is low cost, because a relatively inexpensive method for manufacturing, such as PCB printing, can be used for this kind of application. The third important point is that the design is simple, so it is easy to fabricate. You can simply go to a PCB manufacturer, get it done. And another important factor is that versatility. So, it can be designed for various frequencies and polarization like linear, circular, by adjusting the patch dimensions like length and width, okay, and also the feed method. Now it has also comes with some disadvantages, like the first thing would be narrow bandwidth. Typically this kind of antennas have narrow bandwidth, meaning that they operate well for a specific frequency band only. The gain is another factor. They may have typically bit lower gain as compared to other types of antennas, and the feed network, that is like where the signal gets connected to the patch, can sometimes be complicated depending on the type of polarization. But overall it has got its own positives. As I mentioned here, simple design, low cost, lightweight, low profile, and easy to integrate with circuits and arrays, so makes it very popular. So the design features of patch antennas make it tempting to miniaturize its volume profile by means of an increase in the dielectric constant of the substrate, right. So indeed you can think of the simplest design of a rectangular patch antenna, which is given by these formulas, right. So this is the same design, but here with more technicalities. So here you can see that this is the patch, you have got L, and this is the width W of the patch, okay. So you can see that the length of the patch can be calculated using this formula, C divided by 2 FR, C divided by 2 FR square root of epsilon R effective minus 0.824 into D, epsilon R effective plus 0.3 times W by D, okay. D is basically the thickness of the dielectric slab, okay, plus 0.264, the whole thing divided by epsilon R effective minus 0.258 times W by D plus 0.8, okay. So what is this R, epsilon R effective? That is basically epsilon R plus 1 by 2 plus epsilon R minus 1 by 2 times square root of 1 plus 12 D by W, okay. I will not go into the derivation of this, okay, but here you can see W equals C divided by 2 FR. So you can understand what is FR, that is the resonating frequency, the linear frequency, right. Square root of times square root of 2 divided by 1 plus epsilon R. So from that you can calculate what should be the, you can also see what is LA, that is the pitch length, okay, or the periodicity, or no, LA. From here, sorry, so from this you can also see what is LA, that is the length of the antenna, that will be given by as L plus 6D. So LA is marked as this, okay, the overall length of the antenna. So D is basically this particular thickness of the dielectric slab in between, and WA, that is the width of the antenna, given as W, that is the width of the patch, plus 6 log 16 by pi times D. So LA and WA, this basically gives you the length and width of the antenna. L and W gives you the length and width of the antenna, right. And epsilon R effective tells you about the effective relative effective index, or you can say epsilon R effective is basically giving you the relative effective permittivity of the antenna. Now looking from the equations, one may state that the greater the value of the epsilon R, that is the relative effective permeability, the smaller will be the linear dimensions, that is L and W, right. So that means if you can increase the effective permeability of the dielectric material, that is between the patch and the ground plane, you will get a overall smaller dimension of the patch antenna, right. And this principle leads to the idea of miniaturization of the patch antenna, okay. So people have tried different approaches to increase the relative permittivity of this antenna substrate to decrease the antenna volume profile, right. So this has given a lot of efforts, and we have seen a lot of efforts during the late 20th century for miniaturization of the antennas using this approach. So although miniaturization was achieved in this kind of studies, the performance of such antennas was considerably degraded, okay, and the reason becomes a strong capacitive coupling between the antenna patch and the ground plane. Okay. So, you can not ideally just keep on increasing the permittivity of the dielectric spacer in between, that will also bring in side effects like this. So, what is the solution to this problem? So, in order to decrease this kind of capacitive coupling, okay, it is proposed to replace a homogeneous high permittivity dielectric by a inhomogeneous composite or metamaterial structure with the same value of constitutive parameters. Okay. So, this will allow tuning of the effective permittivity and permeability through individual adjustment in the resonant inclusion dimensions within the unit cells. Okay. So, the initial approaches to antenna miniaturization, people have tried some early designs using double negative metamaterials, then negative permeability materials. They have also tried low effective refractive index metamaterials and so on. So, metamaterials with an increase in the effective refractive index are much less commonly used for creating the composite substrate. Okay. The more logical substitute for homogeneous high permittivity dielectric substrate, but the less commonly used ones are basically those where you have a substrate with some sort of high value inclusions or high value permittivity inclusions, right. So, you can think of some composite metamaterials for that purpose. So, you can use composite metamaterials for miniaturized antennas, okay, and that has been proposed early. So, though there are some attempts done, it remains as a challenging problem in the antenna design. So, we will see some of those approaches today. Okay. So, the current objective would be to develop a miniaturization concept for rectangular patch antennas using metal dielectric composites or metamaterials. Okay. So, what we are going to do, we will focus to create the concept of miniaturization of this rectangular patch antennas on metal dielectric composite or metamaterials with enhanced effective relative permittivity. Okay. So, in doing so, we are considering non-magnetic substrate. That means you keep the real part of the permeability to be 1. So, now let us look into the design more carefully, which I have been showing you for a long time in this lecture. What is that one layer wire composite metamaterial substrate? Okay. So, that is basically the 2D model of the microwave antennas, we will see now. Okay. So, according to the hypothesis, tuning the electric properties of the composite substrates enable one to improve the performance of the rectangular patch antennas. Okay. So, the idea of using a dielectric matrix with a inbuilt wire grid, okay, you can see here, okay, they are making some holes and putting some wires to make it a wire grid. Okay. So, this kind of idea of using a dielectric matrix with a built-in wire grid as composite basically rose when a relevant experiment was reported by Zoganelli's group. Okay. So, here you can see that putting a flat metal dielectric composite structure on the top, and then on that you put this patch antenna, basically can give you improved directivity of the antenna. So, you get better performance from the antenna, right. So, this is how it is done. So, you take the composite sample first, okay, and then you make the holes there, and then in the same sample you basically put some iron wires into the hole, okay, and then you take this composite as your substrate and then print the patch antenna on top, right. So, few things to notice here, that this particular composite has a parallelopiped shape. Okay. So, what is this parallelopiped is nothing but a 3-dimensional figure with 6 parallelogram faces, okay, and It contains wires which are aligned parallel to the patch antennas, so that is also important requirement. Okay, as you can see, this is the substrate, and then you have put the antenna patch on top of this substrate face. So you have these wires which are parallel to the patch antenna. Now the phenomena, what is happening here, was explained in short by Rubin and Shulga. Okay, so Rubin basically expanded the theory for wire grids embedded into dielectric substrates, and in this current study, now you can see what was this drawn. I have never discussed about this, so right now just focus, but till now we have seen this part. Okay, now let us look into this part as well more carefully, that your substrate is not basically a homogeneous substrate. It has got wire holes with iron wires inserted through them, and the axis is basically, these wires are basically parallel to your antenna patch. Right. So in this current study, we will basically present the full wave analysis of patch antenna with one layer wire grid embedded into the dielectric substrate, as you can see here, and the analysis is based on the approach of given surface current and distribution. Right. So consider this 2D geometry of the rectangular patch antenna, which has got a composite substrate, and currently we are showing you in the Cartesian coordinate system. So the patch is positioned here. Okay, so this is the ground that has been marked. So you have this metal, ground metal plane here. So from 0 to 2h, this is the height of the substrate. So your patch is basically positioned here, right? And you are considering the width to be from w. So you are basically having the y axis ranging from minus w by 2 to w by 2, and the length will be along z, which is into the plane of the screen. Okay, so the length is basically from minus l by 2 to plus l by 2. Okay, and we are considering the patch as a perfect conductor with 0 thickness. Okay, now the wires are considered to be non-magnetic. Okay, and this wire grid, as you can see, this is the metallic wire grid. Okay, so they are non-magnetic metallic wire grid, and it is located at a height of x equals h. Okay, so this is the height. So each wire has got a diameter of 2r, right? So it is backed by a perfect conducting wall that you can see here at x equals 0. Now that experiment was done with iron wires. Here we are considering wires made of copper, and we have considered circular cross section. So you can consider the radius of the wire to be r, or the diameter is 2r, and notice that they are all aligned parallel to the z axis, which is going into the screen. And another important parameter is the periodicity of these wires, that is center to center spacing between the wire is considered to be d. Now what are the substrate properties? So first thing is, the substrate is in this region. The dielectric is basically within the region of x equals 0 to x equals 2h, so that in between there, and then it has got a material property like relative permittivity of epsilon m and relative permeability of mu m, right? Now we have to also consider the permittivity of the wires that are included. Okay, so the microwave approximation of the relative permittivity of the wires, epsilon I, is given as epsilon I omega equals 1 plus sigma I divided by I omega epsilon naught, right? So here epsilon naught is basically the permittivity of the vacuum, sigma I is the conductivity of the wire material, right? And then you have an estimate of the relative permeability of the wires, that is mu I, and you can consider it to be mu I omega equals 2 divided by ksr, j1 ksr divided by j0 ksr. So here you can see ks is basically k0 times square root of epsilon I by omega. Okay, that is the wave vector, okay, or the wave number to be precise, and then jmx is basically nothing but the mth order Bessel function of a real variable x. Okay, so So, you can see the Bessel function of the first kind, and these are the orders, okay, and k naught here is basically nothing but the wave number in the free space. So, first you got to estimate your epsilon I omega. From that you can also estimate what is mu I omega, right. Now, let us go into the electromagnetic wave description. So, let us consider a plane monochromatic electromagnetic wave which has got a angular frequency of omega and electric field component of magnitude E naught. Okay. So, we are considering the electric field to be parallel to z axis, right. So, the field is basically excited in such a way that you can see that electric field vector is given as a dot. So, that is like going into the field into the screen, that is along the z axis, okay, and it excites a surface current J on the antenna patch. And another important thing is that the wave is striking the wire grid at an angle of theta, right. So, after having these parameters, so these are the two mediums marked 1 and 2. So, the primary electric field intensity vector E in can be written as E in as a function of x y times z naught. Okay. So, currently you are in this region. So, you can write E naught, that is E in is basically the incident electric field vector. Okay. So, you can write E naught e to the power minus I k 2, that is where the propagation constant of the wave number in medium 2 is being used, x cos theta plus y sin theta times z naught. Okay. Now, k 2, as I mentioned, it is basically k naught only because it is considered to be air or free space, okay, and that is wave number in the second medium, that is for the region x greater than 2h, this region, okay, and E naught is basically the amplitude of the incident electric field and z naught is the unit vector along z axis. So, remember that in the study the time factor e to the power I omega t is omitted throughout. So, we are not carrying that in our work. So, if you also neglect the evanescent waves and you consider the wire radius to be much smaller compared to the periodicity of the wires and also the thickness of the substrate, okay, that means you are basically working in the thin wire approximation. You can safely write that in the first region, that is the first space domain 1, that is where x is between 0 and 2h, you can write E1 as E1 xy times z naught. So, E1 you can write as E naught I e to the power I k1 y sin alpha. So, the wave makes an angle alpha with the x axis. Okay. So, you can also write e to the power this times e to the power I k1 x cos alpha plus r will be basically the reflection that goes in the minus x direction. So, you have r e to the power minus I k1 x cos alpha, right. In the second domain you can write, that is x greater than 2h domain, you can write E2 equals E2 xy times z naught, that is equal to a times e to the power minus I k2 y sin theta times e to the power minus I k2 x minus 2h cos theta times z naught, right. So, that is in this particular domain, and here you can understand that r is basically the refraction coefficient which is given as minus 1 plus g, which is basically this particular constant. Okay. So, we can see here all these parameters are known other than this new parameter zc. I'll tell you what is that. Okay. So, here we know how to calculate k1. K1 is basically square root of epsilon m mu m times k naught, and z1 is basically the impedance of medium 1 that can be given as square root of mu naught mu m divided by epsilon naught epsilon m. So, what is that zz in the previous equation? That is basically the surface impedance of the wire grid, and it is given by zz equals I mu naught omega d divided by 2 pi. So, all these parameters are known, log d by 2 pi r plus delta plus 1 plus I d divided by 2 pi r square root of mu naught omega by 2 sigma I. So, sigma I is basically the conductivity of the material of the wires, and what is this delta? Delta is basically this particular summation. So, half summation m equals 1 to infinity, and then you have these two parameters, right. I am not reading it out. So, this derivation will not go into the details, but if you can use this formula, you can always compute what will be the two electric field. As you can see in this case, you can find out what is your E1 and E2, right. So, in this equation you can also see lambda 1, that is basically the wavelength of the light or the wave that is in the first space region, that is within this particular composite dielectric medium. So, in this equation it is also assumed that d, that is the periodicity, is much smaller than this wavelength lambda 1, okay, and d is considered to be equal to 2h, and that is why your delta becomes negligible when compared to log of d by 2 pi r, and in that case you can find out the limit of delta when the d by lambda naught approaches 0 at d equals 2h. It can be written as e to the power minus 2 pi divided by e to the power minus 2 pi minus 1. So, things get much simplified here. So, we will continue this in the next lecture, okay, and show you further how that can give you the better performance of the antenna by using this kind of a one layer wire composite structure. Remember that in this study we are also neglecting the evanescent wave, and that is why it is unable to evaluate the antenna performance parameters associated with the near field distribution, right. So, with this we will stop here, and in the next lecture we will continue from this part, and further we will discuss about the 2D modeling of the microwave antenna that has got this kind of a one layer composite metamaterial as substrate, right. We will go into more details in the next lecture. Thank you. So, if you have got any query regarding this lecture, mention the course name and the lecture number on the subject line and drop an email to this particular email address. Thank you.